Good morning once again to all of you. Today is the fourth day of myself doing this chapter, Structure of an Atom. It is chapter 2. Okay. Now, yesterday, in yesterday's class, I had a double period where the last thing which I did was numericals. I explained you three numericals uh, based on over there calculation of wavelength, okay, using the de-Broglie formula, de-Broglie equation. Okay. Now, today, if you look at the screen, there is one more numerical which I have missed out. Okay, so let me solve this also. If you have got your pen or your paper or your exercise copy, chemistry, please can you copy this question? Copy this question. I'm waiting. An electron. It is a numerical based on de Broglie equation. It is a numerical based on de Broglie equation. Okay, copy the heading also. It is a numerical based on de Broglie equation. Okay, all of you, those who are present, please copy the equation. What do you call question? An electron is moving with a kinetic energy of 4.55 into 10 to the power of minus 25 joules. Calculate its de Broglie wavelength. So that is the question. Have you finished copying the question, my dear boys?
No, sir.
Not yet.
No, sir.
Please copy the question. An electron is moving with a kinetic energy of 4.55 into 10 to the power of minus 25 joules. Joules. So they are asking us calculate its de Broglie wavelength. The wavelength of that electron, which is de Broglie wavelength. Okay. Now, now I think you must have finished copying the question. Okay. Now the
Yes,
solution
sir.
part. Now we know the formula for
Yes, sir.
calculating the kinetic energy of any particle. What is the formula for calculating the kinetic energy of any particle? A particle which is having possessing kinetic energy. What is the formula? Tell me.
Half mv square.
Yes, very good. The kinetic energy to calculate the formula to calculate the kinetic energy of any moving particle is half mv square. So write down in the solution part kinetic energy Ke of the electron, kinetic energy of the electron is equal to the formula over here, half mv square. This is the formula. Now this half mv square, it is given in the question. The value of this half mv square is given as 4.55 into 10 to the power of minus 25 joules. This is already given. Okay. Now what is the de Broglie's equation which I have discussed yesterday in the previous class? The de Broglie's equation is like this: lambda is equal to h by mv, small m, small v. This v is the velocity of the particle or the electron. So here in this equation there is v. Okay, and mass of an electron, we know mass of an electron is 9.1 into 10 to the power of minus 31 kilogram. Okay, so now what we have to do over here is make this v square subject of the formula and calculate this value of v. Okay, so in the next line what I will do is I will get the value of v. V will be equal to 4.55 into 10 to the power of minus 25. This 2 goes up, so multiplied by 2 divided by m. M is the mass of the electron. Yes or no? M is the mass of the electron. So it is 9.108 into 10 to the power of minus 31. Now this was v square. So I bring the square on the other side. So this becomes everything raised to the power of half. Raised to the power of 1 by 2. Okay. So that is, now upon simplification, the value of v, I will get approximately 1000 meter per second. Okay, I will get approximately or exactly it comes to 999.6 meter per second. That is the velocity I have obtained. Now we go ahead to get the de-Broglie wavelength. Therefore, the de-Broglie wavelength lambda is equal to h by mv. This h stands for the constant which is called Planck's constant divided by mv. Okay. Now value of h is 6.626 into 10 to the power of minus 34 divided by m. The mass of the electron again 9.108 into 10 to the power of minus 31, and the value of v is over here, velocity of the electron. So I put this over here, 999.6. Now in class 11 ISC board, we are allowed to use the scientific calculator. Okay, so by using the calculator, if you simplify this further, you will get the answer 7.28 into 10 to the power of minus 7 meter. Okay, so this is the de-Broglie wavelength. So we can write a sentence over here. Hence the de-Broglie wavelength of the electron is 7.28 into 10 to the power of minus 7 meter. Okay, please copy this working. I'm waiting. Hello.
Yes, sir.
Done, boys? Have you done, boys? Hello?
Yes,
Finished, boys?
sir.
Yes, sir.
Okay. Did you understand the working? Did you understand the working?
Sir.
Okay. So now let us move further in this chapter. Okay. Now read this on your screen. The Heisenberg's uncertainty principle. Read it in your mind, all of you. Read it. So there is one question over here in the first sentence only. This principle is also called indeterminacy principle. The Heisenberg uncertainty principle is also called as indeterminacy principle. One marks question or a half marks question. Now the statement which is given below, it was articulated in the year 1927. It was written down by a German physicist, Werner Heisenberg, that the position and the velocity of an object cannot both be measured exactly at the same time, even in history, even in theory. The very concept of exact position and exact velocity together, in fact, they have no meaning in nature, in reality. So, that is how the principle was stated. It was stated and it was given to the world of chemistry for understanding and for learning further. Okay, where you can see Heisenberg principle states that it is impossible, it is never possible to measure or calculate exactly both the position and the momentum of an object. At the same time, we cannot know the position or the momentum at the same time. You can know either one of them. If you know the position, then you lose the momentum. If you know the momentum, then you will lose the position. That's why this principle is called Heisenberg's uncertainty principle, and it is based. They will ask you the question. It is based on what? The Heisenberg's uncertainty principle is based on what? It is based on wave particle duality of matter. Now, this principle was, stated. It was explained to make the world understand that for microscopic particles like electrons, which are revolving around the nucleus, round and round in different orbits and shells, it was necessary for the world to decide and come to know where is the electron, at what time, where is it, or what is the velocity with which the electron is moving. So that is how this principle was stated. We can get a rough estimation of the location of the electron by using the Heisenberg's uncertainty principle, which has been explained. Now, let us look at the next slide over here regarding the Heisenberg's uncertainty principle. There is a formula which you can see. Delta x means uncertainty in position, and delta p means uncertainty in momentum. Now, momentum means product of mass and velocity. Product of mass and velocity. Delta p. This is the what you call momentum. Product of mass and velocity is called. It is called momentum. Okay. Now, the product of the uncertainty in position with the uncertainty in momentum, it is greater than equal to h by 4 pi, because the movement of electrons, it is in a circular fashion in a cloud, that is also equal to h by 2. Now, the more accurately you know the position, the smaller delta x is. The less accurately you know the momentum, that is the larger delta p is, and vice versa. So that means if you know the position, then you're going to lose the momentum. If you know the momentum, then you're going to lose the position. So at one time, you can know any one of them more accurately. Okay. Now that was the Heisenberg's uncertainty principle. So delta x into delta p is greater than equal to h. This h, there's a slash over there. This slash means what? Slash means h by 4 pi. H by 4 pi. Now this equation is coming under the study of Heisenberg's uncertainty principle. Okay, now moving to our next slide over here. It is given in detail. So let me explain this paragraph, which is a very, very important paragraph, which will help you later on in a study of higher chemistry as well as in the competitive examinations. Because I have seen plenty of questions, concept-based questions from this topic over here, the Heisenberg's uncertainty principle. Now, ordinary experience provides no clue of this principle. It is easy to measure both the position and velocity of, say, an automobile, our school bus, or our two wheeler, or our school vehicle, small vehicle, because the uncertainties implied by this principle for ordinary objects are too small to be observed. That means for big objects, we can get the position also, we can get the velocity also, we can know. Okay, but but the complete rule stipulates that the product of the uncertainties in position and velocity is equal to or greater than a tiny physical quantity or constant, which is called h by 4 pi, where this h is a Planck's constant. I am trying to explain you the equation of the Heisenberg's uncertainty principle, which is delta x into delta p. We know delta x into delta p, that is momentum, greater than or equal to h by, it is 4 pi over here. So I'm trying to explain this equation to all of you just now, and this Planck's constant value is given roughly only for the exceedingly small masses of atoms and subatomic particles does the product of the uncertainties become significant. It becomes important over here. Okay, now any attempt to measure precisely the velocity of a subatomic particle such as an electron will knock it about in an unpredictable way, so that a simultaneous measurement of its position has no validity. So if you get the velocity, then position you're going to lose. I have been telling again and again. If you get the position, then you will not be able to know the velocity of the electron or the subatomic particle. This result has nothing to do with inadequacies in the measuring instruments. The technique or the observer, it arises out of the intimate connection in nature between particles and waves in the realm of subatomic dimensions. So here, this principle was basically designed and it was given, articulated for the study of location of the velocity and position, or the momentum and position of only subatomic particles. You can apply this concept, this principle to huge bodies like vehicles or automobiles, okay, where we can get both the position and velocity. But that is not important for us. What is important is this can be accurately applied for very small microscopic particles only. Now, moving to the next slide over here, the uncertainty principle arises from the wave particle duality. I have been telling you several times. So, if the question is asked, on what basis was the uncertainty principle articulated? So, answer has to be wave particle duality. An electron, a subatomic particle, is behaving like a wave also, it is behaving like a particle also. Every particle has a wave associated with it. Each particle actually exhibits wave-like behavior. The particle is most likely to be found in those places where the undulations of the wave are greater. That means highest point. Okay, that is the crest, and the lowest point, that is the trough, or most intense. The more intense the undulations of the associated wave become, however, the more ill-defined become the wavelength. That means we will get the wavelength, irregular wavelength, okay, because of that, which in turn determines the momentum of the particle. Momentum means the product of the mass and the velocity. When you are climbing a hill, definitely your velocity will become less. Okay, that you have to keep in mind. Its associated particle, while having a definite position, has no certain velocity. A particle wave having a well-defined wavelength, on the other hand, is spread out. The associated particle, while having a rather precise velocity, may be almost anywhere. So, the particle having a velocity which is very accurate, may be anywhere. We cannot get that velocity, what you call the position exactly, if you know the velocity. A quite accurate measurement of one observable involves a relatively large uncertainty in the measurement of the other. So, this is an important sentence over here, boys. A quite accurate measurement of one observable involves a relatively large uncertainty in the measurement of the other. That means if you get velocity accurately, then you are uncertain about the position. So this is one point which you have to keep in mind properly. Okay, this is very important point over here. Now,
Sir,
yes,
So we do not need to know the reason for this
The reason is for,
uncertainty.
see, very, the reason is, see, the microscopic small particles like electrons, no, they are very, very small. They are very, very small, isn't it? They are not big like automobiles or buses or trains. No, they are very, very small. So you can get any one of them, because since the particles have wave particle nature, no, the particles have wave particle nature. That is why
Yes.
if you are able to get the position, if you are able to get the position, you will not get the velocity or the momentum. Or if you are able to get the momentum of that electron, then you will not get the position. That is what I am trying to say. Are you getting it? Are you getting it? That is the
Yes, sir.
reason. That is the reason. Because the particle is a subatomic particle. So if you look at this slide over here, the uncertainty principle is alternatively expressed in terms of a particle's momentum and its position. The momentum of a particle is equal to the product of its mass times its velocity. Thus, the product of the uncertainties in the momentum and the position of a particle equals h by 4 pi or more. This is what I have been telling you from that time. Delta x, that is position, uncertainty in position, into delta p, uncertainty in momentum. This delta p is like this, m delta v, because velocity may change, mass is constant, it doesn't change. So here, that is why the product of the what you call uncertainty in position and the uncertainty in momentum is equal to h divided by 4 pi or more. The principle applies to other related conjugate pairs of observables subatomic particles such as energy and time. The product of the uncertainty in an energy measurement and the uncertainty in the time interval during which the measurement is also made also equals h by 4 pi or more than that also, because you see in the equation that is greater than or equal to h by m, it is 4 pi, sorry, h by 4 pi. Okay, now the same relation holds for an unstable atom or nucleus between the uncertainty in the quality of energy radiated and the uncertainty in the lifetime of the unstable system as it makes a transition to a more stable state. That means every particle which is moving, it will always try to acquire a stable state, whether it is moving or not. A convenient atmosphere, a convenient cloud around the nucleus where it is more stable. So that is to be taken into consideration, because all subatomic particles, if you talk about electrons, which are moving around the nucleus, okay, they behave like waves, they behave like particles also. So that is why, that is the reason why this uncertainty principle was articulated. Now, after you have understood these two things, the de-Broglie's wave particle nature and the Heisenberg's uncertainty principle, now it is the right time for all of us to understand the quantum mechanical model of the atom. If you look at these diagrams, this is how the model of an atom, according to the quantum mechanical concept, has been explained, and today we will try to follow this. Because in the center you will find the nucleus, and around the center, around the nucleus, we will find electrons in the electron cloud. The wave function predicts three-dimensional regions of space, 3D, where electrons are likely to be found. Okay, so that these are the regions where electrons are likely to be found. Okay, these are the regions. Okay, now if you look at the second diagram over here, this is according to the Bohr's model of an atom. Okay, in the center there is the nucleus, and there are orbits or orbitals or shells or subshells containing the electrons continuously moving according to Bohr's model. But today, according to the quantum mechanical model, electron cloud are the orbitals where electrons can be anywhere around the nucleus in an atom of an element. Okay, so this color code is there, electrons. Okay, this is the color code for the neutron, this is the color code for the proton. So this is the main basic foundation for understanding the quantum mechanical model of an atom. Now moving further to one more similar diagram, the enlarged one. The quantum mechanical model of the atom is Schrodinger treated electrons as waves in a model called the quantum mechanical model of the atom. So Schrodinger's equation applied equally well to elements other than hydrogen. So you can see over there, this Schrodinger equation is applied equally well to elements other than hydrogen. The wave function predicts a three-dimensional region around the nucleus called the atomic model. So this is the main concept over here for the quantum mechanical model of the atom. Okay, now have a look at this slide over here. The quantum mechanical model. Schrodinger used a mathematical equation to describe the behavior of the electron in a hydrogen atom. Okay, so this is supposed to be the quantum mechanical model where in the center there is the nucleus and around the center there will be electrons in the electron cloud having nodes or nodal planes. Okay, now quantum mechanical model describes electrons in atoms based on equation which is called Schrodinger equation, which I'll explain you after some time. Now first let us understand what is that. What is Schrodinger equation? Now if you look at the Schrodinger equation on the next slide, you can see this equation which you see is just for the purpose of visualizing is it in chemistry, because in chemistry we don't deal with the solution of this Schrodinger wave equation. We just have a look at this equation and we just try to understand the importance of this equation. Okay, so coming back to the previous slide over here, in the Schrodinger wave equation you see del square psi by del x plus 8 pi square m by h square e minus v psi is equal to 0. This v is potential energy, this E is energy, this x is position, this psi is a Schrodinger wave function. Okay, this del square is second derivative with respect to x, because in mathematics you're learning derivatives. Okay, now let's come back to the previous slide. Here we can see what is Schrodinger wave equation, a very important slide for all of you today. Schrodinger wave equation is a mathematical expression which you have seen already in the next slide, describing the energy and position of the electron in space and time, taking into account the matter wave nature of the electron inside an atom. It is based on three considerations. The three considerations are, they are classical plane wave equation, which I have shown you, Broglie's hypothesis of matter wave, and conservation of energy. That means energy needs to be conserved. We cannot destroy energy, or energy cannot be lost. Now, Schrodinger equation gives us a detailed account of the form of the wave functions or probability waves that control the motion of some smaller particles. The equation also describes how these waves are influenced by external factors. Moreover, the equation makes use of the energy conservation concept that offers details about the behavior of an electron that is attached to the nucleus. So, an electron which is very close to the nucleus will possess higher energy and will carry a negative energy, whereas an electron which is far away from the nucleus, it will possess lesser energy, though it will carry a negative charge. Besides, by calculating and solving the Schrodinger equation, we obtain two things over here. One is psi and psi square. One is psi and psi square. Okay, these are the functions which helps us determine the quantum numbers as well as the orientation. Orientation means the shape, or what do you call the position, orientation. What is the shape of that thing, and the shape of the orbitals where electrons are found in an atom, in a molecule or atom. So here I want you all to remember this thing. This psi and psi square help us to determine the quantum numbers as well as the orientations and shape of orbitals where electrons are found in the molecule or the atom. So this is one thing you have to underline and keep in mind. Okay, so if we solve this Schrodinger equation, if we solve this mathematically by using higher mathematics, then we get to know about the different quantum numbers, namely principal quantum number, then azimuthal quantum number, then magnetic quantum number, then spin quantum number. Now, looking at this slide over here, you can understand the wave function which is called psi. This is one wave function, and psi square is another wave function which is obtained by double derivative. Okay, psi square has no physical significance, except that it represents the amplitude. You know what is the meaning of amplitude? If there is a wave, this is the amplitude. So this amplitude is obtained by using what? by using this function, this wave function, which is called psi over here. Okay, now psi square gives the probability of finding an electron at various places in a given region around the nucleus. So that becomes very, very important sentence. This psi square gives what? Probability of finding an electron at various locations in a given region where? Around the nucleus. It is thus possible to identify regions of space around the nucleus where there is a high probability of locating an electron associated with a specific energy. Okay, so here these are the two important things. One is psi. Psi will help us understand what? The amplitude of the electron wave. It is not so significant physically, but what is more important is psi square over here. This psi square is so important that this is going to help us get a probable location of the electron in the various regions around the nucleus in an atom. So that is why psi square becomes important. Now, an important paragraph over here. The wave functions provide the regions around nucleus in which the probability of finding electron is maximum. These regions are now called orbitals. These are now called orbitals. Now that is the main thing to be understood. So because of the wave functions psi and psi square resulted in the concept of regions which are called orbitals in this chapter under Schrodinger wave equation. Now, the shapes of these orbitals can be explained with the help of Schrodinger equation again, this equation. Moreover, the equation also gives certain specific numbers which are called quantum numbers in chemistry in this chapter, which are very, very important. N, principal quantum number, azimuthal quantum number, small l, magnetic quantum number, small m, and small s is spin quantum number, which specify the location of an electron in an atom. So, what is the importance now? Schrodinger took into consideration the wave particle duality of electrons, and then he devised an equation and solved it mathematically, and then he came to the conclusion that the probability of finding electrons can be articulated, can be located. And after that, on solving the equation completely, he came to the concept of four numbers which are called quantum numbers n, l, m, and s, which specify the location of an electron in an atom. Now you see, in the next slide, if you have a look, there is a plot, a graphical representation between dispersion factor. This is called dispersion factor. Dispersion factor. Dispersion factor from the Schrodinger equation. Psi square r square, because we know psi square is helping us to identify the location, probable location of the electron, and r is the radius, distance from the center of the nucleus to the electron. So this is called dispersion factor. How far is the electron from the nucleus? So this versus distance from the nucleus r, it was plotted for the various orbital, s orbital, 1s orbital, 2s orbital, and 2p orbital. For the 1s orbital, the electrons are very close to the nucleus, okay, possessing energy is high. Energy is what? It is high. When you move to the 2s orbital, the 2s orbitals, they are slightly far away, and then there is 2p orbital, far away, but energy is lesser as compared to the 1s orbital. So this is a probability distribution curve of the electrons for the 1s electron or the 2s electron or the 2p electrons. Okay, now try to remember this graph just for the sake of what you call objective questions, or they might ask you, or we might ask you one mass questions. We will ask you to plot the probability distribution curve of electrons in 1s or 1s, 2s, and 2p orbitals, where on the y-axis you represent the distribution factor and dispersion factor, and on the x-axis represent the distance from the nucleus. So this is how you're supposed to plot the graph, this way. This is what you will do when the question is asked in this case. Okay, this is for 1s, and then for the 2s you can go like this straight away. Okay, and for the 2p, this way, like this is for 2p, this is for 2p, this is for 2s. Okay, so this is how you're going to what you call draw the probability distribution curve of electrons psi square r square versus the distance of this particle electron from the nucleus. So this will carry 1 marks in your examination. So one question I have already given over here. 4 5 questions already done from till here. Okay. Now it is almost time. I think it is already time. So what I will do is I'll just conclude this part quickly, and then I'll continue in the next class. Okay. Conclusions drawn from the probability distribution curve of the electrons. This is an important conclusion. Please try to do not neglect it. The probability of finding electrons at the nucleus is zero. Correct. Number two, the probability of finding electron increases as one moves away from the nucleus. At the nucleus is zero. If you move away from the nucleus, then you may get the electrons. At a distance of 0.53 angstrom, which is called the Bohr's first radius, you will find electrons. The probability of finding the electron is maximum. This distance of 0.53 angstrom is called the Bohr's first radius. And after that, on moving farther from the nucleus, the probability of finding electron goes on decreasing and becomes negligible beyond 2 angstrom. So these are the important conclusions which are drawn from the probability distribution curve which you just now saw in the previous slide. Okay, now I would like to conclude my class here only, and in the next class I will explain you the differences between orbits and orbitals and teach you how to get the values of the four quantum numbers in detail and tell you what are the four quantum numbers L, N, L, M and S in detail and help you solve some numerical, simple numericals based on the concept of quantum numbers. So just hang on over there till I record the attendance for you all. Okay, now looking at the attendance part, I can see there are 45 boys only present today. Okay. Attendance list is downloaded. Now you may leave the class. Thank you so much. Have a nice day.
Thank you, sir.